to talk on topic related to deep neural network. Okay, but you were interested that I should talk on the issues of overfitting in deep neural network and what are the causes and how we can detect it, how we can overcome this problem. Okay, so for this, I'll first discuss one of the simple neural network model, that is your multi-layer perceptron. Okay, and I'll discuss the background, okay, and its working principle. Then I'll discuss the importance of deep neural network architecture over shallow network architecture. Then I'll discuss the problem of overfitting. And then I'll tell you the solutions that how we can overcome this overfitting problem with the help of a method like regularization, augmentation. So let's see this architecture multi-layer perceptron. Most of you may be knowing that in this multi-layer perceptron, you have minimum 3 layers. That is one input layer, one hidden layer, and then output layer. At input layer, the inputs are of a given data. So let's say the inputs are x1, x2, x3, xt. And what you want is output, that is your t1, t2, t3, tk. So in this architecture, we assume that there is a ith node at the input layer, and that is I, and this is your jth node at the hidden layer, and this is the kth node at the output layer. Assuming that the weight between this ith node of input layer and jth node of hidden layer is wji, and the bias associated with this jth node of hidden layer is, let's say, wj0. Similarly, let's say the weight between jth node of hidden layer and kth node of output layer, let's assume it is wkj. And bias associated with the kth node of output layer, let's assume it is wk0. Assuming this, so for a given input x1, x2, x3, xt, okay, the net input reaching at the node, jth node, will be given by, that is wj1 into x1 plus wj2 into x2 plus wj3 into x3 plus wjd into xd plus wj0. So this is the net input that is reaching to the jth neuron. Then what is the output at this jth neuron at the hidden layer? Let's say that the function at this jth node is given by f of net j. Then the output at the hidden layer will be y1, y2, y3, yj. Now these output will go as an input to each one of these neurons at the output layer, and the net input that is reaching to this neuron, kth neuron, will be given by wk1 into y1 plus wk2 into y2 plus wkj into yh plus wk0. And let's say this is given by net k. So for a given input net k at this neuron, the output at this neuron will be given by zk. And that is zk is equal to f of net k. So in this multi-layer perceptron, for a given input x1, x2, x3, xd, we are getting output that is your z1, z2, z3, zk. But for this sample, let's assume that we want to have output t1, t2, t3, tk. So there is a difference between the output given by the machine and the expected output. So what we do in this case, that we compute the error. That what is the error for this set of weights and bias. So we can compute error, and this error can be given by summation of tk minus zk whole square divided by 2. So this is one form of error which we name as a square error. To know what is the actual error for this choice of weights between the expected output and the output given by the machine. So if there is error associated with the network, it means the choice of weights is not correct. So we have to change these weights. So how we change the weights? So you must have been told that there is a method that is your gradient descent method. And there are many variants of gradient descent methods. Okay, you have stochastic gradient descent method, mini batch gradient descent method, you have R-prop method, you have Adam optimizer. These are all variants of gradient descent method. So in this method, once you know what is the error, so we can change the weight W by amount delta W. And this delta W is equal to minus eta del error by del W. So eta is a learning rate, and usually it takes values between 0 to 1. So you started with some random weights of the network. Okay. Now for a given input, you compute what is the output. If this output is different from the expected output, you compute the error. Let's say that error is J. Now, based on this error J, I can compute that how much W needs to be changed. And this W needs to be changed by delta WKJ. And what will be delta WKJ? Simple, minus eta del J by del WKJ. Similarly, by how much amount you change the WJI? That is delta WJI. What is this amount? It is your minus eta del J by del WJI. So I won't go into the mathematical details. You can simply take the derivative and you can find out that delta WKJ is equal to this and delta WJI is equal to this. So there is, I think this is a very powerful method where you want to learn a relationship between input and output, and you have many training samples are given to you, but what you don't know is your weights and bias of the network. And for this, what you do, you start with the random choice of weights and bias, you give the input, you get the output, and if the output observed by the machine is different from expected output, you change the weights. And this process will keep on going till you get a desired set of weights and biases for which the error is less than a particular value, or some terminating condition is satisfied. So that's what you do in multi-layer perceptron. But as the word itself suggests, multi-layer perceptron, it means there can be many layers. So we have started with 3 layers, one input layer, one hidden layer, one output. But you can have many hidden layers. Means between input and output layer, you can have one hidden layer, 2 hidden layers, 5 hidden layers, 10 hidden layers, 20 hidden layers. So then you may be interested to know what is the role of these many hidden layers. Okay. And for this, I'll first talk about one of the research work carried out by Hornick in 1991. And according to this, if you are given some data and you want to learn relationship between input and output, and even if you choose only one hidden layer with sufficiently large number of nodes at the hidden layer, you can learn the relationship between input and output. So I think you can go through this research. It's a very good research, okay, where theoretically it has been justified how one hidden layer with sufficient number of nodes can learn the relationship between input and output. Okay. So let's say we are going to solve a problem where your data is represented in terms of image. Means image has a like I say character that is A to Z. Means one image contains A, other image contain B, other image contains C. So there are, you have many images, and you know that this image contains A, this image contains C, this image contains E. But you want to learn a decision system so that when you show a new image to this machine should be able to recognize which one of the English alphabet is there in this image. Let's say this image size is 100 by 100. And number of characters in English alphabet is 26. So what is the number of inputs at the input layer? So that is your 100 into 100 means 10,000 input nodes you have to consider at the input layer. Since you are solving 26 class classification problem, how many nodes you choose at this layer? 26 nodes. So if the output by the first node is 1 and all other nodes are 0, then you assume that this represents A. While if the second node is giving output 1 and all other nodes are giving output 0, then you assume it is B. And similarly, if the last node is representing 1 and others are giving output 0, then let's say it's representing Z. So given a large number of training samples, you want to learn a relationship between input and output. So as per Hornick, what we can do? We can choose one hidden layer with sufficiently large number of nodes. And let's say I consider 10 raised to the power 6 number of nodes at this hidden layer. So yes, we can learn the relationship between input and output. What we will do? We start with the random weights and biases. We pass on the input data. We observe the output. If the output is not desired output, we'll change the weights. And in this way, we'll be able to learn the relationship between input and output. But what is the problem with this model? The problem with this model is the number of weights which you need to learn is very large. Why? Because you are choosing 10 raised to the power 6 number of nodes at the hidden layer. So the number of connections between input layer and this hidden layer is how many? 10 raised to the power 4 into 10 raised to the power 6. So the number of unknown weights are 10 raised to the power 10. And similarly, the number of biases which are associated is 10 raised to the power 6. Then further, the number of connection between hidden and output layer is of order 26 into 10 raised to the power 6. And the number of bias at the output layer is 10 raised to 26. So you can see that we have to learn a large number of weights and biases. So more we need to learn the number of weights and number of biases, more will be the time needed to learn. And also another important point is that the number of training samples which we should choose should be very large. Because if the number of samples we use for training is less, then you are going to observe overfitting problem. So I'll explain what do you mean by overfitting problem little later. So, but let's understand here, what is the point I'm talking about? I'm saying that the number of weights and biases are pretty large. you will need more computation time. You need more number of training samples. So if the number of training samples is not enough, then you are going to suffer, this model will suffer from overfitting problem. So what is the way to handle this? So then again, there was a piece of research work where it was told the importance of many hidden layers. Why, if you choose 2 hidden layers instead of 1 hidden layer, there will be improvement in something. Why instead of 2 hidden layers, if I choose 3 hidden layers, what will be the advantage? Okay, so again, this piece of research was there prior to 2001, 2000. Okay, so in this, what was told that if you are going to choose, let's say, k number of 2 hidden layers instead of 1 hidden layers, then the number of connections or the number of processing units required to learn the relationship between input and output will be less. Then again, if you choose 3 hidden layers instead of 2 hidden layers, further this number of computational units will decrease. Instead of k minus 1 hidden layers, if you choose k hidden layers, the number of these computational elements will decrease. So what is, in a nutshell, we want to say, by choosing more number of hidden layers, you require lesser number of computational elements to solve the problem. So that is the advantage, that we are going to use lesser number of elements by choosing more number of hidden layers. But what is the problem? The problem was before 2000, we were facing problem. And the problem was of vanishing gradient. That if we are going to use more number of hidden layers, such architecture will face problem of vanishing gradient or vanishing exploding problem. And that's where many research started happening, how to overcome the problem of vanishing gradient. And then many successful research has happened. So what I am talking about in deep architecture is that between input and hidden your output layer, you can have many hidden layers. And that's what we talk about deep architecture. So what we said, that if you have deep architecture, definitely you require a lot of weights, lot of biases. And you have to learn these weights and biases with the help of the training data. So now I am going to discuss that when you develop any model, what kind of problem one can face if you are not careful. So if the architecture involves too many parameters, then you are going to develop overfitted model. Means overfitting problem will arise. Well, if you're going to choose very less number of parameters in the model, then the model may develop underfitted model. Okay, so you have to balance between the two. You have to avoid overfitting, but at the same time, you have to be careful that you are not developing underfitted model. Okay, so now we will see that how we can overcome both this problem. But one, you can say, thumb rule you must use, that is that more you will be using the training data, less will be the chance to develop overfitted model. Okay. So now let's take one of the regression problem. And now here the objective is that you want to predict the price of a house. So what are the factors that because of which the price of a house increases or decreases? So I think if you all agree, if the size of the house is bigger, then the price will be more. If the size of the house is less, then the price of the house will be less. This is one of the important factor. Okay, what is the size of the house? Then there are many more factors also. How many rooms are there? How many bathrooms are there? How many, you can say, what is the size of the kitchen? Then at which floor this house is situated? Then what is the crime rate of that area? Then you maybe what is the education level of that area, whether education facilities are good in that area or not. What is the pollution level of that area? So there are many factors that uh, impact the price of a house. But at present, I'm taking a very simple situation to show it graphically. That let's say I have a training data, okay, where I plot along x-axis size, and size I represent in terms of feet square, okay. Okay, square feet. What is the area of the house? Okay. So on x-axis, I'm plotting a square, that is area, and on the y-axis, I'm plotting the price. Okay. Now, let's say these are my training samples. That for this size, this is the price associated. For this size, this is the price associated. For this size, this is the price associated, and similarly for other size. And now from this data, I have to learn a relationship between your size of the house and the price of the house. And we thought that this relationship can be captured by this formula. Let's say that it involves only two parameters. And those parameters are theta naught and theta 1. So what I am saying that the price of a house with size X is given by theta naught plus theta 1 into X. But I don't know what is the value of theta naught and theta 1. Okay. So this is, I'm considering a very simple model. So now I can learn this theta naught, theta 1 with the help of my neural network architecture. Means only these two parameters I need to learn. So I have the training data. I know the size of the house. I know the price of the house. So I'll give this data and I can learn what is the value of theta naught and theta. But let's think that instead of this model, I consider another model where the number of parameters involved are not one or two, but there are three parameters. And these three parameters are what? Theta naught, theta 1, and theta 2. Same thing. From the training data, I need to learn the value of theta naught, theta 1, theta 2. And now let's think about another situation where I assume that the relationship between the price of a house and the area is given by the formula, let's say theta naught plus theta 1x plus theta 2x square plus theta 3x cube plus theta 4x4 plus theta 10x raised to power 10. So what you see, what is the difference between these three? The first model, I am using very simple model, only two parameters, two unknown parameters. Another model with only three unknown parameters. Another model with I am using 11 parameters. I need to determine the relationship between these two parameters, these two variables using some given training data. And this training data is same for all the three models. And let's say I use neural network architecture. I use the same principle, gradient descent method, and I am able to arrive, let's say, theta naught and theta 1 for this model, and similarly theta naught, theta 1, theta 2 for another, and similarly for this. Now let's see this happens. And for so I have learned theta naught and theta 1, and now it is giving me this kind of relationship. So I now, for my future data, this X, the model will predict that this is the value of price. Okay, so for this X, the price will be given by along this. So I can compute this. So I have learned this decision boundary. Okay, and I learned this relationship, And now for a given X, I can use this, you can say your curve, and I can find out what is the value of the price on this Y-axis. Similarly, for this, I'm getting this. Similarly, for a given X, I can compute what is the value of the price of the house. Now, for this case, I'm getting this kind of learning, it will be there. And now I can find out for a given X, what is the price of the house. So what you find, what is the difference between these three kinds of model? So you see that this is your underfitted model. And this is your overfitted model. And this is the right model which is there in between this. Means if you are using too less number of parameters, you are going to develop underfitted model. And if you are going to use too many parameters in the model, you are going to develop overfitted model. So how we can see during experiment that we are developing underfitted model or overfitted model, so that we can judiciously choose the model which is not computationally very complex, but at the same time it should not be very simple model also, but it's not capturing the relationship between input and output. Okay, so what is the way by which we capture that you are developing overfitted model or underfitted model? So one thing you will always see that if the number of features to represent the data is very large and the number of training samples is very less, in general you develop a overfitted model. So what is needed is that the number of parameters in the model should not be very less, but at the same time, it should not be very large. Okay. Now, to solve this, okay, so you have to understand the term bias and variance. So what do you mean by bias and what do you mean by variance? So in this model, I use the word and I explain. I see that there is a high bias. And in this case, we are getting high variance. So neither I want high bias, neither I want high variance. While there is a trade-off between bias and variance. So if you decrease bias, there will be increase in variance. While if there is an increase in variance, there is a decrease in bias. Okay, so they are related. So you have to make a balance between the two, that is bias and variance. So first of all, let us understand what do you mean by bias and what do you mean by variance. So bias stands for what is the difference between the output which is you are observing and what is the truth value. So the output given, what you expect to learn and what is the truth value. So the difference between the two is said to be a bias. While variance talks about what you expect to learn and what you learn from a particular data. But the problem is what you expect to learn is not known to you. What you are observing is you are given truth value. You can see what you are learning, but what you are expected to learn, this is not known to you. This is not given to you. Okay, so you just think about that there is this is a bull. Okay, yeah, you must be saying if all those shooting events, there is a bull, and the shooter has to shoot and focus on this red area. So if more bullets strike this red area, it means the performance of shooter is very good. And also another important point is that while shooting, these bullets can strike throughout on the this bull. The more is the scatterness, we say then the shooter is not good. So his scatterness should be less, and the most of the bullets should strike this red region. So when we say that a shooter has, let's say, shooted maybe n times strike this bull, and if all the bulls are striking this red region, circular region, then you are saying that you have low bias and low variance. Why we say it's low bias and low variance? Because expected was that you should hit this bull red area, and truth is also red area. Okay, so the difference in the two is very less, so you have low bias, and this scatterness among the striked bull is very less, so you have low variance. I think this is the ideal situation we want to have. Okay, but there can be another situation where you can see that scatterness of the bullets is there over all this region, but the your deviation from this bull is less. So we say that is low bias but high variance. But in this case, what you are saying, most of the bullets, the scatterness is less, but it's away from the bull point, main bull point. So you say there is a high bias but low variance. And in this case, you find that most of the bullets are away from this bull region, and scatterness is also large. So I think even this is not good, even this is not good, even this is not good. The best situation is this, where you should have low bias and low variance. But mathematically, it can be shown that the bias is square plus variance is constant. Okay. So if you decrease bias, variance will increase. And if you increase bias, variance will decrease. So you have to choose a balance between the two so that neither bias is more nor the variance is more. Okay. And so how to observe this? So you take the data and you divide this data into training and test data. So if the performance on both training and test data is very good, if you say that the performance on training data is very bad, it means you have high bias. If the error on training data is very small, but there is a high variance in the case of your test data, means that error between error on test data is large, then we say that you are developing overfitted model. So in the first situation, you find that the bias is balanced, bias and variance are balanced. When your training and test error both is less, then we say that neither you are developing underfitted model nor you are developing overfitted model. Okay, so I'm saying that when both error is large on training and test data, so that shows that you are developing underfitted model. While when you see that your error is less on training data and error is also less on test data, then you are saying you are not developing overfitted model. So, but if the error is less on training data, but error is more on test data, it means you are developing overfitted model. Okay. So in nutshell, what we are saying, if error is large on both training and test data, you are developing underfitted model. Then what is the other conclusion? if the error on training data is less, but error on test data is very large, it means you are developing overfitted model. Now the question is how to design your model that you are not developing overfitted model. Okay, so before talking about this, I am again showing example of, I shown earlier overfitting in regression problem, but now I am showing overfitting in classification problem. Let's say you want to find out that whether this person is suffering from brain tumor or not. Okay, so whether the person is having brain tumor or whether the person does not have a brain tumor. And let's say there are two features, and those features are age and tumor size. And now I'm plotting the training data in this two-dimensional graph, okay, where you are saying that this blue color shows that the person does not have tumor, while red point shows that person is having tumor. So you have to find out a decision boundary which can separate these two class of data. So red cross are for persons with brain tumor, while blue triangles are showing the persons with no tumor. So again, I'm showing three cases of examples, that is for underfitted, overfitted, and right-fitted. So when you are considering lesser number of parameters in the model, so you may come across such kind of situation. So what you find? That you find on this side, there are samples which are misclassified. And similarly, on this side also, there are red plus samples which are on this side, which should not have been there. Okay, so you find, ideally, I would have liked that all samples above this decision boundary belongs to this red plus, and all samples below this decision boundary should belongs to blue triangle. But you find that there are some samples of red plus which are on this side, and there are some samples of plus blue triangle blue triangles which are on this side. So there are many samples which are misclassified. But instead of this, if I choose this situation, you find that the number of samples which are misclassified has decreased. Okay, and while in this situation, I think there is not a single samples which is misclassified. So ideally, it looks that this is the best model. But what exactly sometimes we see that when we fit such model with which involve more number of your parameters, if you are choosing complex model to build, so in fact you are overfitting the model because the features may contain some kind of noise. Okay, so to overcome this problem, so what is needed, that you should not choose lesser number of parameters, but at the same time you should not choose overfit more number of parameters. Okay, now, so now the question is, let's say I go back to my first problem, that I want to predict the price of a house. And I'm saying that the price of a house depend upon many factors, maybe size of the house, number of bedrooms, number of floors, the age of the house, average income in the neighborhood, what is the kitchen side, number of bathrooms, then pollution level, then there can be many factors. Okay, so you have, let's say, 100 factors, but the number of training samples available to is very less. So there is high probability that you are going to develop overfitted model. So then what is the way out? So the way out is regularization. So if you have lesser number of parameters, then chances of overfitting is less. But if you're choosing less number of parameters, you may develop underfitted model. So then what is needed is that you allows more number of parameters, but at the same time, you should have a control on these parameters. And how you can have a control on these unknown parameters? By using an extra term, which will act as a penalty. So I am saying that there is an error associated with my, what is the error on my training data? But also at the same time, I'm using a penalty term. And what we are penalizing is, if the value of this theta j is large, then this error will be large. While if I choose theta j in such a way that this theta j is less, but at the same time, this theta j should be chosen in such a way that the error on the training data is also less, then you are able to avoid overfitting. Okay. So you have to choose theta j in such a way that the one which is important, that should be given non-zero values or higher values, while those which have are not relevant, the values of theta j should be very, very less. Okay. Okay, so now we are saying, by including this regularization term, we want to learn theta in such a way that both error on training data and this penalty term should be as small as possible. Okay. So now, this regularization offers you, so it attempts to guide solution that you are not developing overfitted model. Means you are allowing more number of parameters, so definitely it is not going to develop overfitted model. But now by controlling these parameters, okay, you are able to assign the weights values in such a way that the error on training data is less, but at the same time, the values of this parameter is appropriately assigned. And we'll prefer that we use this, penalize the use of parameters to prefer small weights. Why we are saying that it should be assigned small weights? The reason is that, so this I have shown with, let's say, instead of square error, if I choose cross entropy error. Okay. So this type of regularization, we say L2 regularization, L2 norm. Okay. So when you take a square of all the weights involved with the network, it means you are using L2 regularization. There is another regularization method also, which we talk about L1 regularization, where we take this, instead of W square, we choose absolute value of W. Means we add all the absolute weights of the network. Okay, and we choose the weights in such a way that these values should be assigned value as small as possible. Why we are why we are stressing that these weights should be assigned values less, smaller values? Because larger weight will, if larger weight is associated in the network, then even if you make a small change in the value of the features, there'll be large change in the output. While we want that for a smaller change in the input weight, the output should not change drastically. And that is possible only when the weight is assigned a smaller value. So this is your one of the method to control overfitting. Okay. So what is your, this is one of the well-known practice, Occam's razor. What is that? Among competing hypotheses, means among many different models, which one to choose? We should choose the model which uses fewest assumptions, which use lesser number of parameters. And at the same time, these parameters should be associated with lesser values. And that will allow us to develop robust model, means robust against noise. Okay. So so this was one way of regularization to control overfitting. So what are the two methods we have talked about regularization? One, by using L2 regularization. In L2 regularization, we will talk about summation of square of weights of all the weights associated in the network. In L1 norm, this W square will be replaced by absolute value of weights. Okay. All right. Okay. Now there is another way to regularize. Okay. So that we avoid overfitting. And the another method is your dropout method. So first of all, let us understand what actually we do while we develop a neural network architecture. In all the good practice, what we say that whenever we start with your architecture, we start with the random weights. Then the question may arise, why we start with the random weights? Why we don't start with predefined weights? So there is a reason. The reason is, let's say if I assign the weights with all which are all same, all weights are same, means all these weights are same. In that case, let's say there are 5 into 3, means 15 weights are here, and I'm assuming that all these weights are same. And let's say I assign these weights to be equal to 1. What will happen? For the same input, the net input at this neuron will be same, and the output will also be same. So for the same input, this is also giving the same output, this is also giving the same output, this is also giving the same output. So we are learning the same output, and again these weights, these inputs will give the same input and will give the same output. But what actually we want? We want that you should be able to learn different, you can say, patterns associated in the data. Means each one of these nodes should learn distinct pattern. They should not learn the same pattern. But what we are observing here, they are learning the same pattern. By giving the same output at these hidden layers and the output these hidden layers, what we are saying, we are learning the same pattern. We are not learning distinct patterns which are associated in the data. And that is the reason we start with random weights. So when we start with random weights, this node will learn different pattern, this node will learn different pattern, this node will learn different pattern. Again, these weights are different. So yeah, again, we are learning different patterns. And then using these different patterns, I am able to compute the output. So you always initialize the weights randomly. Okay. Now, so we always start the network with random weights. Okay. But what happens? You consider one model. You started with random weight. Now you start another model, start with random weights, and now both will give you different outputs. So every time we train, our output can be slightly different. So how we take advantage of this different output? Sometimes what happens, we are suffering from one disease. So we visit a doctor and he has given some opinion. And let's say he suggested that you have to go for surgery. So what we do? We usually visit another doctor. And now when we visit another doctor, doctor says, no, I think I can treat you with medicine itself. So you feel little relaxed. But again, to take third opinion, you visit another doctor. And if the third doctor is also saying that your disease can be treated with medicine, you get a big relief, and then you take medicine. Or sometimes what you see that because 2 out of 3 are saying that it can be treated by medicine itself, no surgery is required. So you go for decision what? That you go for medicine. You don't go for surgery. So you are using voting strategy. The majority decision you are taking. Based on majority, you're taking decision. Another is that sometimes what you do, you visit a doctor which is at local place, and you have visited another doctor which is at district level, and let's say you have visited a third doctor, let's say which is one of the best doctor in the country. So do you give same weight to these three doctors? No. So you associate different weights to these three practitioners. Now that is now you are taking decision based on weighted output, so weighted average. Okay. So what now I'm talking about is that instead of training network only once, let's say we are trained the network 5 times, and each one of them are giving different outputs. And now we combine these 5 outputs with some weights, and now we learn these weights also. So this approach is said to be ensemble approach. And what actually has been seen, that ensemble approach decreases the error, or it gives you improved generalization, because it is decision is taken on the basis of average of these error associated with individual models. Okay, so you think about this deep neural network architecture in this way, that you have these input. Okay, and let's say this is the one output architecture, this is one model, output is here, this is giving output of another architecture, this is giving output of another architecture, this is giving output of another architecture, this is giving output of another architecture. And now you are giving you are combining the output of all these 5 networks to take the decision on the basis of ensemble of these 5 networks. So you can think about your deep learning architecture in this fashion. But in this process, what is happening? We are increasing the number of weights and biases in the network. And what we have discussed, that if your model will have more number of parameters, more number of biases, and in general, you have lesser number of training samples, you may develop overfitted model. So we have learned regularization approach through L1 norm, L2 norm, but there is another strategy which we talk about dropout. So what we do in dropout? So this is a new way of regularization which has been suggested, and now people are using mostly in your deep neural network architecture. What we do, that in this, what we talk about, at the time of training, a certain neurons does not participate. Means you ignore certain, means this cross neurons are not considered for learning the relationship between input and output. So only the remaining, which without cross, are participating. And now with the help of this, we learn what is the error. And based on this error, we update the weights. So what will happen in this situation? Only those nodes which are important, which are learning relevant information, they will be associated with the appropriate weights, while other nodes will be associated with the lesser weights and biases. Okay, so means you are assigning lesser weights to non-performer, non-important nodes in this dropout strategy. So what we do in the training, we divide the training sample into many batches. So now for a given batch, what we do, we ignore certain number of neurons. And when we are dropping this number neurons, then both incoming and outgoing edges are not considered from these dropout nodes. And based on this, we update the weights. Okay. So now neurons become less dependent on the outcome of connected neurons. And now in this process, it forces the network to learn more robust features that are useful to more subset of neurons. Okay. And it is also considering an ensemble network to improve the So now another important point is it is cheaper to train. So this is another form of regularization to control overfitting. So what we do in dropout method, we randomly, sometimes for one mini batch, we randomly choose a certain nodes which will not participate. For another mini batch, we consider again we choose a subset of neurons which will not participate. So this will allow to focus only on those neurons which are going to be crucial to learn a relationship between input and output. Okay. Now, what is the another way of regularization? You have learned L1, L2 regularization. Another way of regularization is that you use dropout. Another method is that you give more data to the model. Okay, you provide more number of training samples, so that we achieve through data augmentation. So data augmentation is another kind of regularization. Okay, and what we do, we generate samples which are similar to the training samples. So means we are creating artificial training samples. And all those who are familiar with your convolutional neural network architecture, so convolutional neural network architecture is also a kind of deep learning architecture. There we use a concept of pooling. So what we do, we reduce the size of the feature map by using max pooling, min pooling, L2 pooling, okay, average pooling. Okay, so that is another way of avoiding overfitting. Okay, I think that's all from my side. So what I have discussed, why there is a overfitting problem. So overfitting problem will arise in a situation where the network involves no more number of parameters, but you have lesser number of training samples. Then how you can observe overfitting? You will find you can observe overfitting by finding out what is the error on training and test data. If the error on training and test both is large, you are developing underfitted model. When error on training data is less, but error on test data is large, it means you're developing overfitted model. How we can reduce overfitting? So you can use regularization method such as L1 regularization, L2 regularization, combination of these regularization, which we say elastic net, or we can use drop net, or we can use augmentation, or you in the case of convolutional neural network, you can use pooling. Okay, I think I stop here. So if you have some query, I can take up those queries.
Yes, sir. There is one query in the chat box.
Okay, so why don't you allow the participant to